Welcome back, friends. We're in our last unit, second lesson. We are going to kind of talk again about what we saw in our first lesson, which was our parent function for the exponential and how to transform it. But we're specifically going to talk about identifying whether it's growth or decay. And we're also going to get into regression, which is part of the application portion of these exponential functions. I am going to preface by saying we will need a calculator eventually in this lesson. You don't need one right away, but you will need one eventually. So for the first part, we really hit on this in our 8.1 lesson, the difference between the growth model and the decay model for an exponential function. We talked about that the exponential pair function is a base raised to the x power. If that base is greater than 1, then it is going to show growth, right? And we saw that with our transformation in the chart. We said anytime we plug in 0 for x, we would get 1 no matter what our base is. Anytime we plug in 1, we would get that base back. And if we plugged in -1, we would get 1 over that base. And so it would give us this model where this is 0, 1, etc., etc. We talked about how it would never cross or touch the value of 0, so you do have a horizontal asymptote there. For decay, we also did some examples showing decay, but again, that's if your base is going to be between 0 and 1. So keep in mind that for both of these, your base is positive. Your base is never going to be negative. If there's a negative in front of that base value, that is just the transformation reflecting over that x-axis. Your base will never be negative. But if we have a base between 0 and 1, like a third or a half or 3/4, then that is going to show decay. So it's going to look something like this. And again, we know that, let's say we do have that 1/2 that fits between 0 and 1, we would still have the point 0, 1. Now we would have 1 comma the base, which is 1/2, and then -1 would be 1 over the base, so 1 over 1/2 would reciprocate it, and we would get 2. And so then that shows our decay model. We are going to talk about this format of exponential functions today, y equals a times b to the x power. And we talked about in our transformation that a value would be some kind of vertical stretch or compression, which is absolutely true, but it also shows us the initial amount, because if you think about it, no matter what exponential function we have, growth or decay, we will always have the point 0, 1. But if we have an a value there, a vertical stretch or a vertical compression, it will affect that value of 1. And that is acting as our y-intercept, which is always considered to be the initial amount. So it all ties in together, okay? And again, both of them have that horizontal asymptote of y equals 0. You'll always have a horizontal asymptote for an exponential function. Just like we said, based on the transformations, it might not always be at y equals 0. So we're going to start off really easy, and we just want to identify if the model is showing exponential growth or decay. So remember, it's all based on what our base value is. Anything greater than 1 is growth, and anything less than 1 but bigger than 0 is going to show decay. We also want to sketch a graph and label 3 points. These are going to be the 3 points that I'm easily going to label, just because they're the easiest to get and most likely not the biggest or not the smallest. So I'm always going to use the x values of 0, 1, and -1. You're more than welcome to use the 2 or the -2 or really anything, but remember those values can get very, very big very quickly or very, very small very quickly. So here we go. In the first problem, we want to identify what the base is, because that'll tell us if it's growth or decay. So in the first problem, our base is 3. That's bigger than 1. So this is showing growth. So I know it looks something like this, where this is 0, 1, 1 comma the base, and then -1, 1 over the base. Boom. Easy as that. Next model. My base is 3/4. That's less than 1 but bigger than 0. So that's showing decay. So it's going to look something like this. Again, we'll have the 0, 1 comma whatever our base is, and then -1, 1 over the base. Well, 1 over 3/4 is just going to reciprocate that fraction. So then that becomes 4/3. And of course, that mimics what we're seeing on our graph. The second one, remember, your base is what's being raised to the power. So the base is 3/4. So this is going to be a decay model. However, we do have an A value there of 2. So that's the initial amount, or you can think of that as your vertical stretch. So originally we would have the points 0, 1, 1 3/4, and negative 1 4/3. However, there's that vertical stretch. There's that initial amount. So all of your y values are going to get multiplied by 2. We already know this because of our lesson yesterday. So really this is going to be 0, 2. 3/4 times 2 is going to actually be 3/2. And then 4/3 times 2 is actually going to give us 8/3. And so something like this. And then the last one, our base is 5/4. So be careful. Sometimes when we see a fraction, we automatically assume it's decay. But 5/4 is a number bigger than 1. So this is a growth model. Oops, there's no initial amount. There's no A value. So back to 0, 1, 1 the base, and negative 1, 1 over the base, or the reciprocal of that fraction. So see, that's easy, especially after yesterday's lesson. Okay, this next part is that E number that we also talked about in our last lesson. We mentioned that it was called Euler's number. So remember, that's pronounced Euler, not Euler. And sometimes it's also called the natural number. The only thing you needed to know in yesterday's lesson was that E was approximately 2.7. But we're going to show you a little bit more in detail how it's 2.7 or how we got to that approximation. Because remember, E is very, very similar to pi. It is an irrational number, which means it goes on forever and ever and ever and never repeats itself. But it is a constant. E is always the same thing. Just like pi is always the same number. It's about 3.1415, right? So E is very, very similar to that. So there's actually 2 ways we can estimate the value of E. The first way, and this is where you'll need a calculator, the first way is using this model of 1 plus 1 over x raised to the x power as x approaches infinity. So the bigger the value of x, the bigger the value of x, the closer we get to the exact value of E. We're humans. I don't think there's a way that we could ever compute the exact value of E because that would be a lot of digits, but calculators and computers obviously can do it in milliseconds. But this is what it looks like. All right, we have x. So I have the values of x at the top, and we're plugging in those values of x's into this formula. So 1 plus 1 over x raised to the x power. So we're just going to start off with 10. If we plugged in 10, 1 plus 1 over 10 raised to the 10th power, we would get 2.5937. And I'm just copying this straight from my calculator. If I plugged in 10 squared, which is 100, so if I did 1 plus 1 over 100 raised to the 100th power, I would get 2.7048. If I plugged in 1,000, I would get 2.7169. Notice I want to write a couple of digits after the decimal so we can see that change and we can see how it's closer and closer and closer it's getting to a specific value. 10 to the 4th, which is 10,000. If I plug in that number, I would get 2.71815. If I plugged in 100,000, then I would get 2.71827. And if I plugged in 10 to the 6th, which is a million, we would get 2.71828. So as you can see, the larger our value of x got as it approached infinity, and we got really big, we got up to 1 million, we are getting closer and closer and closer to a specific value. All of them obviously lead with a 2, so 2. And then again, the bigger the value of x got, the second digit, or the 10th place, became a steady 7. Then we noticed that the third digit, or the 100th place, was always a 1. Then we saw it was always an 8, and then you'd see it always be a 2, etc., etc. This is a good enough approximation, this 2.718, and obviously if you're just trying to use E to freehand a sketch of a graph, 2.7 is perfectly fine as well. If you're plugging into the calculator, like I said, there is the E button on the calculator. If you're using the Casio, E is going to be in a yellow color, that offset color, because you do have to press shift first. But it is above the natural log button. So the button that looks like this, that's an LN, I think it's above the open parenthesis button. It'll say E to the X in that offset color, like yellow or whatever it is. But so you'll press shift and then that natural log button, and you'll get E on your calculator. If you just want to know the value of E, you can obviously plug in E to the 1, and it'll spit out this this decimal that goes on and on and on and on and on forever. But like I said, we're going to use this approximation of 2.718. Another way to estimate the value of E is using this sequence of factorials. So if you don't know what a factorial is, that's what that exclamation point stands for. I'm thinking you probably saw it in geometry, but not quite sure. So a factorial actually takes the digit and multiplies by every digit prior to that. So for example, 4 factorial is actually equal to 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. So if we added all these up in our calculator, going to the highest number we could possibly think of, then we would get that very, very close approximation of E. Something else that's very unique about E, which you won't need this year, but if you're taking pre-cal and then calculus before you get to college, or even whenever you get to college, a unique thing about the function of y is equal to e to the x, so that is a exponential with a base of e, is that the slope at a point on the graph is the same as its value. So let's get just a rough sketch of that. If this is our e to the x graph, let's say I pick the point right here. If I wanted to calculate the slope that is tangent to that point, so like this, the slope of this line is actually the same as the value of that point. Or if I wanted to calculate the slope here, it would be very, very close to 0 because this point is very, very close to 0. So like I said, that's kind of getting into calculus, like derivatives and all that fun stuff. So just kind of keep that in the back of your mind if you know you're going that route. If not, then it's just something cool that you learned today. All right, so what we're going to do now is we're actually going to go back to some of our exponential properties, and we're just going to simplify these expressions. So the first thing we see is we see e to the third times e to the seventh. Well, e is a number, but they're the same. These bases are the same. So what happens when you multiply the same base with exponents? You add your exponents. So this is now just e to the 10th. Now that is a number that you could approximate, but the goal of these three examples is just to simplify, not to get an approximation. In part B, remember the properties of dividing. So we can divide the numbers by the numbers, and then the e to the 13 divided by e to the 12. Well, 25 divided by 5 is 5. E to the 13 divided by e to the 12 is just e to the 1. And if your exponent's 1, it is understood. You do not have to put it. Because remember, when you divide, you subtract your exponents. And then lastly, we have 2e to the negative 3x, all of that raised to the 5th. So remember what happens when you raise a power to a power. You multiply. The thing to remember here is that also the 2 is also being raised to the 5th. So really this is 2 to the 5th times e to the, well, what's negative 3x times 5? Negative 15x. Now let's simplify this. This is going to be the same thing as what's 2 to the 5th? Well, that's 32. Over e to the 15x. Why over? Because there's a negative. Remember, when I have a negative exponent, it gets reciprocated. So this is going to move to the bottom, but it stays 15x. I cannot simplify that any further. So that is my final answer. Okay. So here again, we see another way to write our exponential functions, and that is using the base of e, and that's why you see it being called the natural base, because most of the time e is also called the natural number. So again, we have a very, very similar look to the function. We have y is equal to e to the x, which is very similar to what we saw of y is equal to the base to the x. So remember, e is a number bigger than 1. So this is a model showing growth because my base is bigger than 1. So it's going to look like this, where this is 0, 1, 1, e, and then negative 1, 1 over e. And we can approximate those values, but you know that it's going to be showing this type of model. In the second one, we have y is equal e to the negative x. We actually already talked about what happens when your exponent is negative. That is a certain type of transformation. And that is a horizontal flip, which is a reflection over the y-axis. So if I take this model, here and I reflect it over the y-axis, I'm going to get something that looks like this, right? And so obviously this is now showing something that looks like decay. Now let's think about plugging in some x values. If I plug in 0, e to the negative 0 is still e to the 0, so I'm still getting the 0.01. But if I plug in 1, this is actually now going to be e to the negative 1, which is 1 over e. And if I plugged in negative 1, that would be e to the negative 1, which is just positive 1. So then I would get e. So this is the exact pattern we would have seen for the decay model. So what this means is that when your base is e, you can actually look at the exponent to decide if it's growth or decay. If it's a positive exponent, it'll show growth. And if it's a negative exponent, it'll show decay. So it's a little bit different than what we saw here. This was if the base is bigger than 1, it's going to show growth. And if the base is less than 1 but bigger than 0, it's going to show decay. So just a new way of looking at growth and decay based on what your base is. So let's practice that. All we need to do is determine if the function represents growth or decay. So notice all of our bases here are e. So if we have e to the negative 4x power, we know that this is going to show decay because it's a negative exponent. If we have a base of e, remember that 0.3 is not part of the base. That would be a vertical compression. That's your initial amount. That e is being raised to the positive 5x power, so this is going to show growth. And then again, we have a base of e. 7 is just the initial amount or the vertical stretch. And this time it is being raised to a negative 0.45 times x power. So this is also going to show decay. All right, again, using some exponent properties, we want to take y equals 2 raised to the 2x and rewrite it into another form of y is equal to a times b to the x, which is what we're going to be seeing most often. So let's remind ourselves of some exponent rules. I know that when I have exponents being multiplied together, then that means I raised a power to a power. So if I were to rewrite this, I could say, well, this is really 2 squared to the x power, because then that would be a power raised to a power. And what do? We multiply them, and that would give us 2 to the 2x. But now we can simplify because I know 2 squared is just 4. And so now I see that my base is 4, and it's being raised to the x power. My a value now is just a 1. It's understood there. So 2 to the 2x power is actually the same thing as 4 to the x power. Okay, we're going to do the same thing now, but we're actually going to rewrite it a step further. So what we're going to do is we're going to rewrite it into this form of a, the initial value, times either 1 plus r or 1 minus r raised to the x power. So what's inside the parentheses is like our base. So obviously if it's 1 plus a number, that's a number bigger than 1, it would show growth. And if it was 1 minus a number, then obviously that would be a number less than 1, so it would show decay. Here's where you're going to need a calculator again. So what we need to do is we need to rewrite it first. We're going to plug it in the calculator, get a value, and then determine if it's growth or decay. So how can I rewrite y equals a times 2 raised to the x over 3 power? Well, look at your power. Something was being divided. You can rewrite that as 1/3 times x, right? So really, this could be rewritten as y equals a times 2 to the 1/3 power raised to the x. Because power raised to a power, I would multiply 1/3 times x is the same thing as x over 3. Here's where you need your calculator. Plug in 2 to the 1/3 power. You're going to get a decimal. Just approximate it. I'm getting 1.26. So now I can look at it and see, what is my base? It's a number bigger than 1. So this is showing growth. I want to rewrite it so that it looks like 1 plus a number. So that's a times 1 plus 0.26 raised to the x power. The reason why we want to separate it out is because now I can tell you specifically that whatever we're talking about here is growing at a rate of 26%. This R value is always going to be converted into your percent, okay? So 1, meaning it's staying at 100%, and then it's growing by an additional 26%, whether we're talking annually or quarterly or daily or hourly or whatever. Because we could be talking about money here. We could be talking about a bacteria. We could be talking about purchase order. Whatever the case may be. So this is very application based. Okay, let's try this one more time. So the first thing we want to do is we want to rewrite it using those exponent properties. So over here, this is the same thing as y equals a times 0.5 raised to the 1/12 power raised to the x. Because again, power to a power, we would multiply 1/12 times x is the same thing as x over 12. So plug that into the calculator. 0.5 raised to the 1/12 power. You're going to get a decimal that's about 0.944. Well, again, clearly this is a number less than 1, so this is showing a decay model. So I want to rewrite it so that it looks like y equals a times 1 minus what? 1 minus what gave me 0.944? Well, that would be 0.056. So again, now I can tell you specifically it's decaying at a rate of, this is not 0.056%. Remember, to change a decimal to a percent, we would move it 2 places to the right. So this is actually at a 5.6% decay rate. Okay. We're going to do the same process again. The only difference is that now our base is going to be E. We're still going to rewrite it in the same way and determine if it's growth or decay and at what rate. So first thing is to rewrite it. So this would be y equals e to the negative 0.5 times x. So you can plug this in your calculator. So remember, to get e, you're going to shift, if you're on the Casio, you're going to shift and press that natural log button, which is right above the open parenthesis if you're on the Casio. If you don't have a physical Casio, remember there is that VM software that you can get on your iPad. If you haven't done it already, you can go to Schoology and in the second folder, like the content folder or something like that. I forgot the name of it, but it's in there, directions on how to get it. Or if you have another online calculator that you're more familiar to, E is probably on there. So when you type in E to the negative 1/5 power, you get 0.607. So this is a number less than 1, so it's going to show decay. And then we need to figure out at what rate. So remember, we're rewriting this as 1 minus a number, and that number would be 0.393. So it's decaying at a rate of 39.3%. And then one more time. Remember, what is your base? It's just e. The 0.5 is just the initial value, or you can think of it as a vertical compression. So it's not going to affect your answer at all. So we have 0.5 times e to the 0.8 power raised to the x. So in your calculator, e to the 0.8 power is going to give you actually a bigger number. It's 2.226 raised to the x power. Don't worry, that's okay. This is possible. Rewrite it as 1 plus, because it's a number bigger than 1, we already know it's growth. So it's actually 1 plus 1.226 to the x. So think about this. Whatever this application is dealing with, is growing at a rate of 122.6%. Man, if that was a bank account, sign me up right now. That's freaking awesome. Okay. All right. So that's pretty much it in regards to the growth and decay models and how to rewrite and stuff like that. And so lastly, we want to quickly talk about regression. So we want to introduce talking about identifying types of data. And we've actually already done this before. But remember, we have 3 types of data now that we can look at given a graph or a table or values. And that's going to be linear, quadratic, and exponential. So we want to look at the inputs. If the inputs are equally spaced, which all of these graphs are going to give us that, so x's are equally spaced, then we look at the y values, the outputs. If it's linear data, the differences will be the same. So we say it's the first difference because we just subtract them and we get the same thing. It's going to be quadratic if the second differences are the same. What does that mean? That means we're taking the difference of the differences. And remember, we've done this before. And then lastly, we're getting into exponential. Exponential is going to give us a common ratio. So if we're multiplying or dividing by the same thing, then that means it's exponential. So, like I said earlier, great news, all of the inputs are already equally spaced, so we don't have to worry about that. So now I'm looking at the outputs. So when I look at A, I immediately see that I'm multiplying by 2 every single time. 0.5 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, so on and so forth. So that means there's a common ratio, which means this is exponential data. Okay. Then I look at B, and I see not the same situation anymore, right? So now let's look at our differences. So if I find the difference between 2 and 0, that would be -2. 0 and 2 is +2. 2 to 8 is a +6, right? Yes. 8 to 18 is a +10. 18 to 32 is a positive. 18 to 32, here's my pregnant brain coming back. Is that 16? That would be 14, right? And then 32 to 50 would be +28. Is that right? 18. Too much. 18. Okay. So those are obviously not constant. They are not the same. That was just the first difference. So this is not linear, and we already know it's not exponential. Let's check to see if it's quadratic. So I want to check the second differences. So the difference of the differences. So -2 to 2, that would be a +4. 2 to 6, +4. 6 to 10, +4. 10 to 14, +4. 14 to 18, +4. Those are all constant, which means this is quadratic data. Okay. In C, I'm looking at the outputs. I know that they're not being divided by anything equal, but I noticed very quickly that 15 minus 3 is 12, minus 3 is 9, minus 3 is 6. So obviously that first difference is constant. So this is linear data. And then when I look at D, I immediately see that I am dividing by the same thing, or I'm multiplying by 1/3. 27 divided by 3 is 9, divided by 3 is 3, divided by 3 is 1. So if there's a ratio, then that is exponential data. Okay. We're going to show an algebraic method of getting a model given 2 points, and then we're going to show you those regression steps in the calculator. So for example 8, you shouldn't need a calculator, but for example 9, you will. So in example 8, we are giving you 2 ordered pairs that are on the graph of the model. What we need to do is come up with the model. So we're going to kind of use a system here. We're going to plug in what we know. If we know that when x is 1, y is 6, then that would look like 6 equals a times b to the 1 power. What I'm going to do is I'm going to solve for a because that's the only thing without like a number attached to it per se. So to get a by itself, I'm going to divide by b to the 1 power. So 6 divided by b to the 1 is a. I can't do anything with that, so I'm going to go to the second set of ordered pairs. So the second set says that when x is 3, y is 54. So y is equal to a times b to the x power. Again, instead of solving for a, what I can do now is I can actually plug in my value of a, right? I'm going to use substitution. So if I do that, I get 54 equals 6 divided by b to the 1 times b cubed. Well, that would really be 54 is equal to 6b cubed over b to the 1, which is just 6b squared. So to solve for b, I'm going to divide by 6. I get 9 equals b squared. Here's where it gets a little fun. Not fun, but just kind of funny because it showed up in a lot of your memes whenever you posted your math memes. When I take the square root of b on both sides, you should already know the answer is b is going to be plus or minus 3. I would hope that that's what you're shouting out. However, you have to think about what these variables are representing. B is representing a base. And can our base of an exponential function be negative? No. So when I take the square root of 9, I don't want to say it's plus or minus 3. I only want to get the positive value of 3. So the base for this function is 3, which means if I plug that back in and solve for a, 6 divided by b to the 1, so that would be 6 divided by 3 to the first power, which is just 3, is 2. So my model is y equals 2 times 3 to the x. Please remember that this is not the same thing as y equals 6 to the x. We cannot do that. Please leave them separate. If you need to put that base in parentheses to kind of, if it's like a identifier for you, that's totally fine, but leave them separate. Our base is 3. Our initial value is 2, or if you want to think of that as your vertical stretch. Okay, let's try this one more time. When x is 1, y is 10. So 10 is equal to a times b to the first power. So that means 10 divided by b to the 1 is a. I also know that when x is 3, y is 40. So 40 is equal to a times b cubed. Plug in our, plug in our value of a. So 40 is equal to 10 over b to the 1 times b cubed, which is going to be 10b cubed over b to the 1, which is just 10b squared. Solve for b, divide by 10 first. 4 is equal to b squared. Technically, b would equal a plus or minus 2, but b, our base cannot be negative. So b is just 2, which means a would be 5 if I plug it back in. So our model is y equals 5 times 2 to the x. So both of these were showing growth because our base was bigger than 1. Okay? And lastly, like I said, we'll do the exact same thing, but with more data because we're going to plug it into the calculator. So I'm pretty sure you have done regression before. So like I said, you will need a calculator. Hopefully you have a Casio with you or you're using that emulator. If not, depending on the online calculator that you use, the steps may be a little bit different. So you probably want to go that VM software if you don't have a handheld Casio. But basically what I'm giving you is a table with x values and y values. And this is an application, so it's kind of like a word problem. But it's talking about a store selling trampolines. So the table shows the number y of trampolines sold during the xth year that the store has been open. So in the first year the store is open, they sold 12. In the second year the store was open, they sold 16, so on and so forth. Now, this problem tells us specifically to write an exponential function that models this data. So we already know that this table is showing exponential data. What we don't know is the initial value, the base, or the rate, or anything like that. So to get that information, we're going to go to our calculator. We're going to go to Menu, Statistics, which is option 2. And once you're there, you may have to clear something out if it's not cleared out. But in your L1, in your list 1, you're going to enter your x values, which is just 1 through 7 in this case. And in L2, or list 2, you'll enter in those y values, so the 12, the 16, etc. Because we already know it's exponential, we can jump straight to this step. So going straight to exponential regression, you can calculate, which is F2, press regression, which is F3, choose exponential, which you'll have to go down and you'll have to do F6 and F2 because it's not in there, so you have to arrow over. And then you'll get the model. You want the model A, B to the X because that's what the problem says. That's what model we've been using, right? And so it'll give you some answers. It'll say A is this, B is this, etc., etc. It will also give you an R and an R squared rate. The closer that R squared is to 1, the more precise and the more accurate and the better your model is. Okay. Before we talk about those values, I do want to tell you that you may not know what kind of data you have. If this was a quiz or a test and we just give you some data, it might not be exponential. It might be quadratic. It might be linear. It might be whatever. So in order to see what kind of model it is, you'd want to go to that scatter plot. So you would do the same first step, enter in the x, enter in the y in those two lists, but instead of going straight to the regression, you'd want to see your scatter plot. So you'd go to graph, and then once you see your model, obviously, not obviously, but hopefully, you'd be able to easily identify if it was linear, quadratic, or exponential. Then you could go to calculate and choose your appropriate regression type, exponential in our case. But with all that being said, you should see, if you plug this in the calculator, you should see that your A value was about 8.46. Your base, your B value was 1.42, so obviously showing growth, which we already knew based on the data, and raised to the x power. Then what we need to do is actually answer this question. It says, so we wrote our exponential function that models the data. Initial amount, 8.46. Growth rate of 42% because our base is 1.42 raised to the x power. Then it says, do you think this model can be used to predict the number of trampolines sold in the 15th year? Well, of course it can. I can keep continuing this list and go to 15, which means all I need to do now is plug in 15 for x. And if I plug that into my calculator, I should get an approximate 1,628 trampolines. Now, here's where you can kind of take a step back and think about this. You can think about it in two ways. In regards to the numbers that we see in this table, in this chart, is 1,628 comparable to what we're seeing in year 7? And if we just think of like doubling year 7, would 1,628 trampolines be realistic? Probably not. However, if you think about it in regards to a good business practice, maybe by year 15, they got it down to the perfect science. They don't have any manufacturing issues anymore, all those kinds of things. And in a new business year, there's always kinks. So that's why the number of trampolines wasn't as high. But as you can see over time, it's getting higher and higher exponentially. So maybe this is a good thing. Maybe, like I said, they just fixed everything they needed to fix. They got their costs down, their profits up and all that fun stuff. It kind of reminds me of Shark Tank a little bit, but maybe, this would be a dream for that business owner. So, okay, that's just a little side note, but that's it, guys. So practice, 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 and we'll see ya again next time. Bye.